before we actually dive in and we go into the recording session, how many of you guys are currently running IPv6 or are in the midst of rolling out IPv6? Okay, and so how many of you are still looking at and trying to figure out what you're doing with IPv6? Okay. It's actually a better percentage than usual. Usually in the States I get about a third of the audience at most who is rolling out or who has already rolled out V6. So I like dealing with network groups. Closer. You guys hear me fine? Good. So I'm Paul Ebersman. I work with Infoblox, and my full-time job is actually dealing with IPv6, teaching, speaking, working with our engineering department. So I'm assuming that all of you at this point are quite comfortable with and have done quite a bit with IPv4 networks. And the thrust of this is basically to go through what are the operational differences in V6, what kind of things do you need to think about, what do you need to do in your network designs and plans to deal with those differences so that you're using the better parts of V6 and avoiding some of the problems and hopefully avoiding some of the things that we've all learned to live with in V4. So the first thing that we have is, of course, what are you going to see when you start doing V6? Obviously, you're going to see insane numbers of addresses, 340 undecillion. And undecillion is one of those sort of useless metrics. Nobody really understands what that number means. But we all understand it's huge. And of course, you know, big, long, beefy addresses that look really pretty and are a whole lot of fun to type. And one of the other things that we get a lot of is you do an ifconfig and you look, and suddenly you aren't just seeing one IP address per interface. You are seeing lots of different interfaces. And there's sort of a lot more magic that happens in the network automagically is how we usually describe it, that isn't static configuration and isn't quite your classic DHCP v4. So in the conceptual model, the 7-layer model we all have grown used to, IPv4 and IPv6 functionally act the same. All of the stuff below them layer just the same, and all of the stuff above them more or less work the same. There is nothing magic, there is nothing better or worse in any of those upper stacks. For better or for worse, HTTP will still be the same regardless of which IP version you're running. There are some things that are going to be noticeable to you and are good things. You know, I'll certainly be talking about a lot of the problems with IPv6 as we go through, but things that I think the IETF really got right. From the routing standpoint, there are a lot of things that over time are going to give us much more efficiency. We have fixed header sizes now. It's no longer a variable length packet. All of the various options are done in an extension chain, and all of the router-specific options are at the beginning of that chain, which means that routing code can snap a fixed packet size. You know how many packets you can hold in a certain amount of memory on the card, and you can read into the extension chain only as far as until you hit the first non-routing relevant option and stop. All of that means that your per header processing can be much more efficiently coded. There are flow labels now, so you don't have to impose some kind of virtual flow-based routing on top. It's actually now built into IP potentially, which should make flow-based routing in QoS much easier to code. One of the other great things about V6 is middleware boxes, things between the sender and the receiver of the packet that felt that they were somehow empowered to play with our packets. Load balancers, application gateways, all of the other things like classes, middleware boxes, stateful firewalls, have all been the bane of our existence in debugging. And one of the things that they have traditionally done a horrible job at is dealing with packet fragmentation. In v6, intermediate devices do not fragment packets any longer. You now have something called PMTU, MTU discovery, and the sender is told by intervening boxes that packet is bigger than I can send to my uplink. I need the packet scaled down to this size, down to a minimum of 1280 bytes. So only the sender now fragments the packets. There is also no checksumming. Because there's checksumming in UDP and TCP and in other upper layers, there is really no value in doing checksumming, but it's yet one more thing that our routing devices had to deal with in the past. So when you get to those routing and switching efficiencies, those flows, those lack of fragmentation, lack of checksumming, we're going to be able to have much cleaner network stacks. And when we get the IPv6 code down into the silicon on the NICs, we're going to see some performance increases. And with the bigger vendors, you're already starting to see that. There are also efficiencies at the network layer. There is no longer broadcast. You're not just spewing stuff out that everybody in the world has to look at. There are essentially unicast, one single sender to one single receiver, and multicast, which has one sender to multiple receivers. Multicast is broken up into groups, and you subscribe to the groups that are useful to you. So there is sort of a broadcast. There's an all nodes multicast, and any node that is on the network should respond and subscribe to that group. But there are an awful lot of things, and we'll talk about this with DHCP, where suddenly you don't have to just spew packets out at layer 2 and see who decides to pick it up, or spew things at layer 3 to an all zeros or an all ones address and see who picks it up. You can be very selected in what you actually listen to. There's also no longer ARP and reverse ARP. What we have now is various types of ICMPv6. Neighbor solicitation, which says, hey, I've got this address, is anybody else using it? And neighbor discovery, so you can find out who else is on your local subdomain. All of that is taken care of as part of ICMPv6, and again, it is done as multicasts, so only the relevant parties who need to listen will have to process that in their network card. There are 3 basic types of addresses. Everything breaks down in IPv6 to you have a type and a scope. Unicast is one sender, one receiver. Symmetric communication. Multicast, one sender can send to multiple recipients who have all subscribed to that type of message. Anycast is usually described as a type. It really isn't. Anycast is exactly the same as it is in v4. It's really a routing trick, where essentially you inject the same host address, the equivalent of a /32, a /128, everywhere, and then routers pick whichever one is topologically closest as the actual host that gets the packet. Scopes say where that address is relevant. Types say what kind of sender, what kind of receiver. Is it one-to-one, one-to-many? Scope says where do I send it? Link local is essentially your local or broadcast domain. Global unicast, which is public address space. Unique local, which is more or less analogous to RFC 1918. And we have various transitional styles of addresses that are used as we move from a primarily v4 network to a primarily v6 network. We also have various other miscellaneous things, site local, which has been deprecated. There are certain reserved types of addresses, just like there are certain reserved well-known ports. More detail. Link local is your virtual wire. It is a single VLAN. It is your, even though there is no broadcast, thinking of it as the broadcast domain in the v4 sense is a perfectly logical way of dealing with it. Everybody in that domain hears and sees all of those packets. There is a special address reserved for it, FE80. So when you look and you do an ifconfig on your Unix box or ipconfig/all on your Windows box, and you see all of the addresses that you have, in all cases you will have an FE80. This is what you use for all your communication locally, including to your local router. When you send packets out your default gateway, you will have a source and destination address with your address and the remote end, but the next hop address will be the link local address of your router. It's very similar if you have nothing but link local to the IPv4 stuff in v4, the 169.254, where if you are doing DHCP and you can't get anything and you come up with a null network, you get an IPv4 network. The other thing that you will find unusual is that your link local address is usually FE80 and then an address derived from your MAC address, and I'll go into that shortly. But it means that effectively you are a multi-interface host. You use that same address on all of those interfaces. There is a zone or scope that is added to that link local address so that you can specify that particular one. So you'll see something like FE80 : a bunch of alphanumeric gobbledygook %EN1 if you're going out your EN1 interface. But when you start looking, that's another one of those sort of culture shocks of why do I have the same address on all of my interfaces? Global unicast is what I expect most people to be using for most things. This is one of the reasons we are all excited about v6. There's enough actually unique, globally routable space to do everything you need. So we should use it. And that is global unicast. I believe in using it everywhere. And I'll talk about this several times through here. I'm not a big fan of private addresses, and I'm not a big fan of NAT. There will be customers and instances and reasons why you may have it mandated, but if you can avoid it, you should. Unique local is that RFC 1918 equivalent, and it has all of the same features and problems that 1918 has. It is not globally routable. That may be a security feature for you, it may not. It is not unique. Because the address space is so large, people will say, oh, well, statistically speaking, the odds of two companies choosing the same ULA and having a collision when you then have a merger and acquisition is small. To which my response is, human beings are lazy. Everyone in the world is going to take the first ULA prefix, slam : 1 on the end of it, and use it. Just like everyone in the world uses 192.168.0.1 or 1.1. So you can register it, which is interesting, because if you're using private address space and you don't want to disclose what you have or what your address range is, registering it publicly does seem rather odd to me. But if you are worried, 6x.net, an IPv6 provider, does have a registration service, so you can register your private space. It is the replacement for 1918 in the regard it is private, and it does have all of those features. You should filter it at all routers. It should, in theory, never be able to get past your network, even if somehow you leak it. You should never leak DNS for it, et cetera, all the 1918 stuff. If you have to use it, it's there. As I said, there are a lot of addresses for every single interface. That's great. We have plenty. There are perfectly legitimate reasons why you might wind up with multiple prefixes that you actually have that you are using. Other cool things, you no longer have to run an active routing protocol in every end host. Every end host with an IPv6 stack has it built in that it gracefully deals with multiple default routes and will test them periodically to see if they are usable. You can rank them by preference, so it will use one in preference unless it goes away. And the client will happily deal with the other default routes if one of them does disappear. Suddenly, we don't have to do HSRP or VRRP or run OSPF on the host, yet we have all of the resiliency of multiple routes. And we can specify it from the routers, not from the hosts, so the networking group gets to control how the clients use our network. It also has what I refer to as quiescence. When I get a prefix, and I get an address in that prefix, I am told that I can use that address. One of the things I get when I'm told that prefix is how long that particular prefix and address is usable, just like a DHCP lease. So even if I use Slack instead of DHCP, I effectively get a lease time. When I have an open connection, it will keep that address using. So if I go through and I had : 1, and then suddenly for some reason I go back, I get my address, and I have : 20 as my address, what I will do is I will start using : 20 as my source address for all of my new connections. However, I will not drop my : 1 connections. I will keep it in the routing table. I will mark it as deprecated. Don't use it for anything new, but keep all open connections running until that connection closes on its own. When all connections have gone away, take it out of my routing table. So I will accept packet traffic in, and I will quiesce. I will gracefully degrade the connection until it goes away. So unlike v4, where if I change addresses, all of my TCP sessions immediately break and it is immediately visible to my user, in v6, that connection on a deprecated address will stay, depending on the OS, for 1 to 2 days. Now, if you do have something that goes over 2 days, yes, the connection will drop. But in most cases, they'll never notice. So I can have addresses coming and going all the time on v6, and my clients will handle it gracefully, and the users on those host machines will never know that their address has changed underneath them. One of the other things that is different and we'll have to get used to is the, okay, so I have multiple addresses on an interface, and I send a packet out that interface. Which one do I use for my source address? How do it know? Well, there is an RFC that has a whole series of rules for saying, this is how I know. You should read it in detail, but what it tries to do effectively is, if I'm sending to another host on link local, I will use my link local. If I'm sending to something else within my own prefix, and I'm presumably within my company, I will use that address. If I have something called a privacy address, which I use to obscure who I am somewhat on the internet, and I'm going out to someplace that's not within my own prefix, I will use that. So there are rules for what source address I should use. So subnetting. One of the really important things that we have gotten used to, or unfortunate things really, in v4 is we have gotten address space in dribs and drabs and little chunks as we've been able to get them. And when we try and do a subnetting scheme that maps to how our business is arranged, by topology, by department, by security zone, whatever, we don't have enough address space to be able to have our subnetting plan match how we would delegate. So for instance, logically, most of us can probably do that with DNS. We can probably do subdomains and delegate out pieces of our domain space to other people in a way that maps to how we do business. We can do it by hub, we can do it by department, by city, whatever. But we usually didn't have enough address space to match that. Well, at this point, we have enough address space that you can actually have a plan. Not how do I cope with what I was stuck with in the way of leftovers, but how do I do things to make my network self-documenting, to make my ACLs sane and consistent, and to make things a whole lot easier for my NOC and for me when they wake me up at 3 o'clock in the morning to fix something. One of the other things that I emphasize a lot, when you're getting your address space, figure all of your addresses. 1918 space, all of the public space, you have everything. Get enough global unicast address space to do everything in public routable address space. You may still choose to do NAT, but you've got a choice now. And if you choose later that technically the reasons for doing NAT are no longer valid, you already have enough address space in the same range. So you don't have to go and get yet another range of address space. And map your subnets to the way that makes sense for you. Finally, again, we have some control over our own destiny. And think about how you are doing your aggregations by site, by ISP or by RIR region, by geography, by department, by security zone, whatever that is. Think about that and do that. Here is just a sample plan of how you might do things. One of the things that I feel is pretty important to keep in mind, every one of those little characters on that address, the 2, the 0, the 1, the D, B, every one of those hexadecimal characters is a nibble. It's 4 bits. So one of the things you should probably do to make your life sane is make sure that all of your prefixes are on nibble boundaries or divisible by 4, because you're not dividing within one letter. Technically works great, but it's a lot harder to deal with. It's the we are actually going back to the convenience of class-full 8-bit addressing in v4 without CIDR, but we have enough space to actually do it. And so you can go through and you can say, well, 4 bits gets me 16 bits. So in this example, I do everything by my geography. This might be something that a data center provider or a hosting provider might do. So I'm only in 12 cities, so I can fit into my 16. That gives me 4 more cities to grow later on. And so in my 32, which is the first 2 quartets or chunks between colons, that's fixed. So I go into my third one, and the first character, that's a 36, that defines which city I'm in. I can then go down to the second nibble in there and have hubs. So I can actually have multiple hubs or co-location facilities within one geographic area. I discovered that I need at least 100 possible floors for some of my hubs because I have huge data centers. So in this case, I give 2 nibbles or 8 bits, and I am now able to deal with at least 256 floors for every one of my hubs. And then again, I have a large switching fabric, even though I have big switches. So I've decided I'm going to give 8 bits or 256 switches on every single floor. And then, again, every switch might have up to 256 VLANs. And so in this case, I can go through every one of those nibbles, all those bytes, and I can subdivide. So for instance, at the VLAN level, I can say company X is at this VLAN in this hub. That's the Apple. And I can, even if I have the space for it, potentially match the exact same VLAN number in a different hub. I can write little scripts that will carve through and select and go, oh, here's the same security zone. I can match these. So again, you have a chance to actually self-document and make your ACLs easier to machine generate, database generate, and maintain. There are some things that you need to consider when you are doing prefixes. In much the same way that no one will route a longer than /24 in the IPv4 world, and many ISPs won't route anything longer than a 22. Currently, everybody's saying if you're longer than a 48, if you're a 50 or 52, I will not announce that particular prefix. I will only announce a 48. So if you have 6 sites that are geographically distinct with different connectivity, you need to get the next size upper of /44 so you can give a /48 to every one of your disparate sites. The recommendation is to give 64s to all subnets. This is anything that hosts are on. Don't go longer than a 64 for anything that has a host on it because SLAC, or stateless auto configuration, assumes and requires that the rightmost 64 bits is the host portion of the address. And you will undoubtedly find cheap switches and cheap routers and cheap middleware boxes that have already implemented and hard-coded a 64. Don't know of any offhand, but I will buy a beer for somebody if they can prove to me that there is no code out there that is already written that is broken. The only other 2 things that you're going to see other than 64s, RC 6164 recommends that for security reasons, you use /127s for your point-to-point links. Because there are only 2 nodes, there is no neighbor discovery or neighbor cache that can be corrupted. It takes away a security issue. And it's pretty much, if you're already doing /31s for point-to-points in all of your router and switching links, and /32s for your loopbacks, and you're using your IGP, you internally carry all of the loopbacks in externally peering, 127s for point-to-points and 128s for loopbacks, and you're going to be a happy camper. It's going to work just the same. What I usually recommend is that you take a /64 out of your address space for point-to-points and a /64 for your loopbacks per routing domain. So if you have a segmented network where you're in 2 places, you can't obviously put point-to-point links here and here out of the same 64 because you fragmented your network. So give a 64 for loopbacks and a 64 for point-to-points out of every unique routing domain you have. Multi-homing, good news, bad news. The good news is that if you know how it works in v4 and you understand why you would want provider-independent space or not, you still know. Bad news is that if you don't understand how it works and you're not sure which it is, v6 has nothing magic to suddenly make the decision for you. All the same trade-offs apply. In this room, I suspect that what that simply means is, yeah, you already know why you want it in v4, same thing, and the justifications are as easy or easier with v6. The biggest change right now is that in v4, if you have physically disparate sites with no internal backbone, you can try and get an AS and claim multi-home and get provider independent space for all of those, but the RIOs are very stingy about that. If you make that same argument for v6 right now, pretty much everybody, including Ripe and Aaron, is going to say okay. So, Slack and DHCP. This is probably the biggest change in how v6 works versus v4. And Slack is just stateless auto configuration. This is essentially the end nodes configuring themselves instead of having a central authority do it or statically configuring. The way they work is there are what are called RA or router advertisement messages. So all of your router and all of your switch ports on your network now suddenly send out messages to tell your clients what they need to do to configure. Now, the interesting part here is that in most cases now, you either statically configure your network and all of your hosts, or you set them to auto-configure, and then you run DHCP. So if you are doing your network configuration or your security policy checks, you validate that by downloading all your DHCP configurations, looking through them, and seeing if that seems to do what you want. v6, you now need to look at every router and every switch port everywhere on your network to make sure that they are correctly configured to send out routing advertisements with what you want. So that's a pretty big change in how you do things, and depending on how you are set up, different departments may now suddenly need to play together, because your router folks and your DHCP server folks, if they are not the same, both have to do things potentially to get things working with RAs. Interface ID generation. I talked about you take FE80 and you slam this address on it, and that's how you get your link local. What's usually done by default is an EUI64, which basically takes your MAC address, which is 48 bits, runs it through an algorithm that I'll go over in the next slide, and turns that into a 64-bit number, and you just slam that on the end. Now, by default, Windows 7 and Vista will generate a random number instead. You can change a registry value to make them generating EUI64 or not. Servers and Linux and Unix variants all pretty much use EUI64. So what you do is you take your MAC address, and that's the 48 bits, and you cut it in half. There's a cute little thing down here. The 7th bit is inverted to say that this was a global MAC address, i.e. it's a public, registered, legitimate MAC address. I'm not sure why they didn't make that the default case and leave it alone and have the inverted bit be for the exception, but it's the ITF, they like fun. So you invert the 7th bit, you cut it in half, and then you stick FFFE into the middle of it. So for you, the first thing you can do is as soon as you look at a v6 address, if you see that there are 6 hex digits and then FF and then FE and then 6 more hex digits, you can pretty much assume that that's a MAC address and that it's an EUI64 generated. You immediately know that, and you know to flip that bit. And you can then reverse engineer what the MAC address of the machine is from that EUI64. So, Slack, stateless autoconfig. Let's go through what happens when you are coming up. The first thing your machine does when it is trying to come up on a v6 network is it will go through, get its MAC address, and it will generate the EUI64. It'll then take that EUI64, slam it onto FE80, and it will say, okay, that's my link local address. Temporary, I'm not sure if it's usable yet, but that's what I'm hoping that I can use. Then what it will do is called duplicate address detection, or DAD. It will send out a neighbor solicitation ICMP message, multicast, to the all nodes multicast address, saying, is anyone else using this address? If no one answers, it says, this is available, and it will permanently configure it. If this is the classic is you bought a bunch of network cards on sale from somebody in Taiwan, and you discover after you light it up that you got 12 cards, all of which have the same MAC address. So what will happen in that case with V6 is that first machine will come up, and it will say, is anybody else using it? And no one will answer, and it will win, and it will use that address. The second guy that comes up is going to come up. He's going to say, is anybody using it? The first guy's going to say, oh, yeah, I'm using it. Going to run a random number, add that to its EUI64, and then try DAD again. And statistically speaking, because it's randomly generated, the odds of you hitting collisions multiple times, even with 12 machines all using that same MAC address, it's statistically very unlikely that there will be a duplicate the first time, certainly not by the second time. So 2-3 seconds and you're done, and you have a unique address at the link local. The next thing you do is from your link local address, and now you have a legitimate IPv6 address. So no broadcast, because you have a real address. You send out a router solicitation ICMPv6 message to the router's only multicast. So no other hosts, no other servers have to listen or hear it. Only routers that have registered as routers will hear it. They will hear that and they will go, oh, someone needs one. Here is my router advertisement. And it will give them all of the instructions they need to configure and potentially tell them to DHCPv6. That's the other. You don't DHCP anymore unless you got an RA message telling you that you will DHCPv6. So the things that you will get in your RA, you will get the prefix or prefixes that you are allowed to use on that particular interface and for that particular network. And if the autonomous address flag, the A flag, is on, it tells you you are allowed to auto-config. So what you do is, for every one of those prefixes, just like you did with FE80 for link local, you will slam your UI64 onto the end of that prefix. You will do duplicate address detection, and assuming nobody answers, you will then add that to the list of addresses you have. And if you're given 3 prefixes, you will try that with all 3 prefixes until you have addresses in all 3 prefixes. So you could conceivably have link local plus 3 other prefixes, all on an interface. Other things that it includes is the router's link local address, because you use the router's link local as your next hop for your default gateway. And it will tell you how long you should keep that route before you query and see if you should change it. And relative priority. So if you get multiple RA responses back, all of which give you a default gateway, you will look at the relative priorities, sort them, and that's how you as the client will decide which to use. The other things it will have is manage address or M flag, which says get an address from the DHCP server, and the O flag, which says get your other configuration. So conceivably, you could decide to use Slack and auto-config for your address and only use DHCP for things like your DNS server, NTP, stuff for your SIP phone, whatever. Because the RA doesn't give you that information. Now, recently, the RA could send out DNS message information or DNS server information, but many clients still don't support that. So it's probably not robust enough for most environments. You still should probably use DHCP to give DNS servers. The other thing that's a little odd, it's perfectly okay to hand a prefix, let the client auto-configure their own address, and then hand out another address in that same prefix via DHCP. Works fine. Operationally, it's a little funky and probably annoying to troubleshoot, but technically it works. Last thing you'll get is the MTU. How big is the pipe of your upstream? So again, we talked about fragmentation. What you get is you get a packet too big message from any intervening box anywhere along your path that can't throw the packet up its upstream because it's too big. So obviously, you want to know how big the maximum packet is at your first hop, so you don't have to waste time doing that when you first start sending packet flows. Things that are not in the messages, though. You can't get NTP, you can't get all the other information, and only recently could you get recursive DNS servers. So effectively, you can't just DHCP because you can't DHCP without an RA to tell you to DHCP. And you can't just RA because you don't get things like a DNS server reliably or other configuration. So effectively, we are stuck right now with you will run both everywhere. So we will all have to deal with that. There are camps that are trying to make DHCP only, sort of like the I want my DHCP v4 experience in v6, but there's a great deal of obstruction to that move in the IETF. The biggest thing that's missing in DHCP is you can't get a default route, so you have to use the RA for that also. So even if I say A flag or autonomous address flag off, don't auto-configure any of your addresses, and DHCP for everything, I still have to have RA telling me both those things, and I still have to have an RA to tell me what my default route is. So you are stuck with configuring all of your edges, every router and every switch port everywhere in your network, to either turn on or turn off RAs explicitly and have them correctly configured, and you're going to have DHCP servers available or DHCP relays to get you to a server in all cases. Now there are some good things with DHCP v6. No boot P. Woohoo! Boot P was a festering pile. And DHCP v4 is basically boot P with saddlebags, duct tape, and baling wire, and a slew of vendor options because people were too lazy to try and get it legitimately through the IETF. And not surprisingly, the protocol is a mess. This is one of those times where the IETF actually re-engineering it from scratch was a feature. Currently, you have to run v4 and v6 DHCP servers at the same time. There are no dual stack, dual protocol servers available. But they've made that easier. There are new ports. So what you will find on a dual stack DHCP server is it's running 2 daemons, has 2 lease files, and is running on 2 sets of ports. They have somewhat cleaned up vendor options. This is the, I had a teacher who used to talk about the, you can't polish a turd, and if you could, all you'd have would be a shiny turd. We still have vendor options. We still have turds, but we have shined them up, and we have made them a tuple, type, length, and value. So there is now a standardized, pretty consistent box in which we now store the turds. For better or for worse. At least makes DHCP config files and DHCP server code much cleaner to write because it's not this variable length, not predefined object goo that we have with v4, where essentially you get to design data structures in your config files. The other one that's kind of cool is the reconfigure is now secure. In v4, there was a reconfigure, but there was no authentication on how it worked. So anybody could say to everybody in your network, okay, time to get a new lease, and if you could somehow manage to trash the DHCP server and get yourself up shortly, you became the rogue DHCP server on the network, and life was bad. They have a password authentication method for v6 that actually means that the guy that you got your lease from originally is now the guy you're still getting your lease from, and it actually works. So you can actually leave reconfigure on, which means you don't have to wait for leases to expire. You can actually essentially push network changes. So renumbering is now vastly less painful because I can use reconfigure and I can push the change. And all of the clients will happily get the new addresses and they will quiesce. So they will happily use the new prefix, but they'll keep using the old ones on persistent connections. So I could actually completely renumber and my end users might never know that we were on completely different prefixes. You could do it during the day. This is a table. This will obviously be in the slides if you want to get it later. Most of the stuff are analogous. Instead of having what we used to call DORA, discover, offer, request, acknowledge was the sequence for a DHCP transaction. It's now solicit, advertise, request, and reply. And they use solicit and advertise because they are consistent with the neighbor solicitation and neighbor advertisement and router solicitation and router advertisement. What is nice is they have broken some of the functionality out so that you can, in your logs, have a better idea of what's going on. Currently in v4, if you look in your DHCP log, you see a DHCP request and a renew. You don't, unless you can correlate it to other things, you don't know if the request was brand new lease, renewing a lease, or just came up on the network after being slept and checking if the address is still valid. That's now broken out. So Request is only for new leases. It's after you get the advertise you do the request. Renew is exactly that. You know it's a renew now, so you can actually see how many of your DHCP requests are renews and how many of them are requests. You can break them out. Rebind is the, I put my laptop to sleep, I woke it up, but before I use that address, even though my lease is still valid, that prefix may not be valid. Something else may have changed, so I'm going to make sure that I'm still in the same network and the server still thinks it's okay for me to use that lease that is still good. So one of the other things that we have dealt with for years in DHCP is addresses are scarce, so pools are small, so we exhaust our pools. Well, in v6, use the whole /64 for a pool. There's no reason not to. 18 quintillion, 4 billion times 4 billion addresses in a pool. If you exhaust 18 quintillion addresses, there's something seriously wrong with your logging and monitoring system in letting it get that far. It's not a problem of your pool size anymore. One of the things that you do also want to consider, one of the classic stories of IPv6 is more secure than IPv4 because a subnet is a 64, which is 18 quintillion addresses. You can't possibly brute force scan anymore, which is true. If you brute force scan that size of address space, and you could get 1,000 addresses a second queried, it would be literally years before you completed one subnet. That's assuming that you're actually using the whole 18 quintillion. If you are one of those people who sits there and goes, well, my router is .1, and my DNS server is .254, and all of my hosts are between 100 and 250 in my IPv4 address, and so if my address was .225, I'm just going to take my prefix and go : : 225, and that's my v6 address. It is self-documenting, and it's very clean, it's very consistent. It also means that you've reduced the scan size from 18 quintillion to 256 hosts, at which point it's brute force scannable. So you need to make that decision of what you're going to do and make sure that you're actually getting the benefit of using that whole address space. And obviously, 18 quintillion, you should never run out of leases. But I would certainly have a watermark, because practically speaking, just because of broadcast domain, sizes of neighbor cache tables, which are the same as also ARP cache tables, there are practical sizes on switches and routers before they reset, only so much memory in kernels, all that stuff. Reasonably speaking, if you have more than 2,000 hosts in a single subnet, you're probably going to start having some traffic problems. And if you have over 4,000, I would be surprised if you were able to have a terribly functional network. So if you're only using 4,000 of 18 quintillion, it should be an infinitesimally small fraction of your space. So definitely pay attention. If you suddenly notice that even 1% of your space in your pool is being used, something is sucking up addresses and not giving them back, and something is broken. So, failover. Well, failover was really there to solve two problems in v4. One of them is that if you change the v4 client's address midstream, the client would notice and the user would notice. And we did not have pools that were big enough, so we kept running out of pool space. So what failover allowed you to do was have redundancy of two and only two servers, because you had to do them in pairs. It allows you to share those so that even if one server is down, the clients can still get their same address back, so they don't have to change their address. You have that redundancy, and you can get twice as many servers serving that same pool. That's no longer a problem. In v6, we've already found out that you can change addresses willy-nilly, and the client stacks deal very gracefully with it in a very user-transparent way. So changing address is no longer a problem. And obviously, 18 quintillion addresses should be enough for most of us, since that is 4 billion internets worth of address space. And failover is spectacularly fragile if you've used it. It has interesting failure and recovery modes. It requires a lot of care and feeding, and it requires some fairly sophisticated operational procedures for your NOC guys to keep it up. And in most cases, what people really didn't want was they didn't really want failover anyway. What they wanted was high availability. and failover isn't high availability. They aren't quite the same thing. So I personally question the need for failover. Reconfigure. Oh, sorry. You do have to have the client and the server both set to do reconfigure. That's where the server sends out a message and the clients. This is like notify in DNS. It simply takes the refresh timer and sets it to 0 so that you immediately do an SOA query to see if there's a new zone file. Reconfigure simply says, instead of waiting half of lease time before you do a renew request, as soon as you get a reconfigure, do your renew request now. That's what it causes in the clients. But the client has to be configured to do it, and the server has to be configured and know which clients will do reconfigure. It does have security, but because of the fact that there is quiescence now, and because of the fact that you can do this reconfigure, it is quite conceivable that you can do renumberings live and your users won't know. So, one of the other interesting new bits, in DHCP-v4, we use the MAC address in many cases as the identity of the client. And we all do that knowing that MAC addresses are fundamentally flawed. They are really not unique. You know, we have the classic 12 cards from Taiwan all with the same address. You can change it in software. And usually the client picks one MAC address, but we very frequently now have multiple connection machines. My laptop has a hardwired Ethernet, a wireless Ethernet, Bluetooth, and a tether to my phone, all of which it could, in theory, DHCP over. And if I try and use my MAC address for all of those, whoever got there first wins, and then the DHCP server won't give me any more addresses because it'll say that's already in use. So there are a lot of problems with it, but the reality is that the vast majority of all eyeballs on the internet, certainly anybody that has a home broadband connection or anybody that is at a large corporation, the odds are excellent that whoever is running their DHCP is identifying them and logging them and tracking them by their MAC address. So yes, it is flawed, but obviously it is a workable solution for most of us. Now, DUID, which is DHCP Unique Identifier, is the IETF's attempt to come up with something better than a MAC address. It is better, but yeah, in some ways. However, as with all things in computers, they all suck. They just suck in different ways. One of the biggest problems is if you use a DUID that in theory right now per RFC has no relationship to the MAC address, nor can you attempt to reverse engineer the MAC address. You are specifically prohibited in RFCs from doing that right now. So if you track v4 addresses by MAC address and v6 by DUID, you have no way of knowing it's the same machine. And you can't get the MAC address from the DUID. And another bit of fun, the way you get a DUID is there's an algorithm you run. And the first time that you try and DHCP as a client, or the first time that you invoke yourself as a DHCP server, you will look in persistent storage in disk and see if there's a DUID already there. If not, you will use the algorithm and you will generate one. If you're using one of the ISC DH client or DHCPD software bases, you will be looking in the lease file for your DUID. If you are on a Windows operating system, you will be looking in the registry. Once you've done it once, it's written into persistent storage and it's there forever. Which means that even if you change network cards multiple times, as long as your disk is the same, that user is still identified by the DUID. That actually is one of the things that makes more sense. One of the gotchas that they didn't think about, I take a machine that's working and I decide that I'm going to clone this one engineering workstation and build 10 more from my engineering department. I don't think to wipe the leases file. So they will all come up. They will look in the leases file and they will say, I have a leases file and I have a DUID. And they will all try and get an address and be told that DUID already has an address, go away. So you need to make sure that if you want to preserve that, make sure you back it up in the registry or in the disk file. And if you don't want that to appear, make sure that you wipe it out. Otherwise, you'll have interesting transitions later on. So there are some things that really are right. One of them is that there is one single unique identifier per machine, regardless of how many network interfaces it has. But you can actually differentiate with an identity association, an IA, for every network interface. And that pair, that duple of DUID plus IA, uniquely identifies every single interface. So you could actually have all of them DHCP, and the server will know that they are different entities or identities because they all have a unique key. That pair makes a unique key. And there are three types: temporary addresses, privacy addresses. I haven't gone through, I'll just do it very quickly. Because of the fact that EUI64 is trivially reverse engineerable to give you a MAC address, and you use it everywhere you go, a lot of folks at the IETF said, well, you know, if I go and I go to work, and I get an address there, and I get in the logs, and then I go to a coffee house, and then I go to 3 customers, and somehow someone like the government is able to get log files from all of those places, they will know it's me because it's my MAC address in all places. And we don't really like that idea. So what we'd like to do instead is create an address that is randomly generated and changed usually every 8 hours, some as long as 24 hours, but no longer than 24 hours, that you use for unknown connections out to the internet. And so they can only correlate one day of what I'm doing, not weeks or months of where I've been going. So those are privacy addresses or temporary addresses. Non-temporary, which is mildly counterintuitive, but because the addresses that I get from a DHCP server are sort of temporary in that I have a lease. I only get them for my lease time. I don't get them permanently either, but they're not a temporary or privacy address, so they are non-temporary. Prefix delegation is the third, and that's where instead of giving you an address, I can give you a whole range of addresses that you can further carve out. The model most commonly done is home router. I have a subnet that has my home theater. I have a subnet that has my home office. I have a subnet that my kids are on that I want to be able to segregate so that World of Warcraft doesn't torch my voice over IP phone. I have a net for the kitchen, whatever. Okay, giving me a /64 isn't terribly helpful because I need a /64 for every one of those. What you can do is you can do a prefix delegation, and your home CPE gets, say, a /60, which gets me up to 16 /64s that I can then assign myself to subordinate routers in and around my house. So you can actually do a hierarchical routing infrastructure dynamically with prefix delegation. Not much support in routers yet, but that's the goal. So it has a lot of potential. They are still debating how to do it, and the obvious other missing piece is how do you make sure the upstream routing correctly does all the right things, and how do you know subordinate devices do their default routes up correctly? And there's an IETF group called HomeNet that is one of the more active in debating how this is supposed to work. So ICMPv6, that's one of the other changes. You know, in the pet peeves of mine, beyond middleware boxes mucking with my packets and doing stupid things, and NATs making my connection suck, one of the other things that tends to make my life miserable doing networking is security people with checklists of conventional wisdom which have stuff that is plain wrong, has never been right, and has been around for the last 15 years. Like that DNS is port 53 UDP only and TCP is only for zone transfers. Wrong. Never been right, but I still go some places where they go, here's our checklist, and we have blocked TCP 53 because that's insecure. One of the other places that I just see it all the time with v4, we don't know how to block certain parts of ICMP v4 and allow ping to work, so we just disable v4 ICMP everywhere, and we have no security problems. Sure. You have no debugging capability either, but hey, you know, apparently you don't really care about that. Well, ICMPv6, here's some of the things that you can't do if you don't have ICMPv6 enabled. You can't do duplicate address detection, so those 12 Taiwanese cards are all going to sit there using the same address, and you're going to have lots of duplicate IP errors all over the place. Cool. Of course, you also aren't going to have any default routes because there aren't any RAs, because you can't ask for RA messages nor can you receive them, because that's ICMP. So you can't do any Slack. So all you've got is your link local address that you don't know is valid. You can't get packets too big, so what happens, the complete sequence is if I get a packet that is too big for me, I throw the packet away completely. And the only thing I do other than that is send a packet too big, and here's how big my upstream is, back to the original sender. If they are blocking that, they don't get that message. They don't know it didn't go through, so they keep sending packets too big, and I keep throwing them away, and eventually it times out at layers 4 through 7 and breaks. You can't test any form of connectivity. You don't get any form of networking errors. So if you want basically an APIPA-like experience of a local network with no useful servers, no DNS, no default gateway, and probable duplicate addresses running around loose and nothing else that you can do, and you consider that a usable network, more power to you. If, however, you actually want a functional internet, you need to start filtering intelligently. The nice thing is that they have truly surgically described all sorts of types of VM or ICMPv6 messages. So you can be very precise and surgical in what you put in your ACLs and disable things that really are unsafe or inappropriate for you while still having a usable v6 network. And also every so often the IETF surprises me. They're great on protocols, but not so great on operational stuff. They wrote themselves unprompted a BCP RFC 4890 that says, here are what you definitely don't want to block in ICMPv6 if you really want things to work at all. Here are things that you might want to think about. Here are things that most people won't want, but here's what you might want to think about. And then here are things that are sufficiently dangerous or weird that they're okay in the lab, but most people won't. Recommendations are great, and the nice thing is that when you get these security wants with their checklists, one of the few things I've ever found that actually will sway them is waiving an RFC that they are directly violating in front of them. So here it is. Here's your ammo. And security. Pretty much most of the things that you will see in ICMPv or in IPv6 are really very much the same as in v4. The names may be different. There may be some mild changes. But functionally, if you're doing ARP cache corruption and kicking over routers or confusing hosts, it's pretty much the same as neighbor cache corruption in v6. And it's pretty much the same. You have to be able to get a packet onto the local network. You have to have some way of getting into the table. And what will happen is it will usually cause denial of service. There is no disclosure. It just stacks will either slow down or crash. And it's usually pretty damn obvious very quickly. And my contention is that if you have someone who's able to inject multiple packets reliably onto your secure network at link local layer, neighbor cache is not the problem you need to fix first. You need to figure out how the hell they got packets onto your network at all. Did they get physically access to it, or are your filters and ACLs for your intervening routers broken? So most of the things that we see right now and that are potentially problems with v6 are not in any way unique. If you are already working on network security issues and disclosures and vulnerabilities in v4, you will have a new name to learn for v6, but as soon as you associate it, you will go, oh, that's such and such, and pretty much you're going to know what the risk is, what the mitigation is, and how likely it is that someone will be able to exploit it in your network. And there are others. Router header 0 is a new thing that it's actually been deprecated already before it hit the door, but IPv6 has it. All I have to say is loose source routing. You all know what loose source routing is. You know why that can be a problem. Take the wrong path or an unexpected path, they may hit something soft in one of your firewall or ACL rules. So loose source routing is usually turned off everywhere. Router header 0, same. So I could go through point by point by point, but for the most part, what you've already built in knowledge, once you simply learn the new terms and you see the definition, you'll recognize it. Most of what I'm seeing and what I expect to see are simple misconfigurations. People turning on RA messages on a subnet that they really shouldn't have because they didn't know any better. and they cut and pasted a configuration from somewhere else and didn't know what it did. They didn't understand IPv6 well enough, didn't read the RFC, so they filtered something they shouldn't, or vice versa. Most of the things I think we're going to see are things that are done due to ignorance rather than malice or forethought. There are also obviously things with, it's a huge code base. Other than at backbone core router and switch level, dual stack, there is very little wide-scale operational experience with v6 yet. Very little that involves lots of server traffic, very little that involves end-host traffic. We are going to be discovering interoperability issues, ambiguities in the IETF standards, and other things, and just plain broken code and interoperability issues. And we're going to be fixing them. Current track is, right now the IETF meets every 4 months, and at every IETF there is some at least measurable change in IPv6 or DHCPv6 that vendors potentially have to change their code for. When you're talking about large vendors, changing your code every 4 months is like a wind sprint. You know, they can do it once, maybe they can do it twice, but you just know that they're going to crap out in the middle of something and hit some bug somewhere along the way. And many of us who have change control windows and maintenance windows and change control processes and all of the others, and windows in which we can't not touch anything, are going to find it difficult to keep up with those for a while. So that's the other, untested code, pure lack of experience with it, and security stuff. Most of the firewall and intrusion detection and signature-based folks really don't have a complete grasp of IPv6 or have full feature parity between their v4 and their v6 sets. Even more so in some ways than the signature-based, because there are tunneling technologies and other things that are starting to be used that we don't know are a problem. In the same way that 3 years ago, trying to figure out if you had a BitTorrent or too much Facebook usage on your corporate network was very tough or impossible with the gear we had. These days, anybody that claims to do anything signature-based that can't do both of those trivially is obviously not kept up. We will get there with v6, but we are not there yet. There are some things that, of course, everyone says, because my job title is IPv6 evangelist. I get to be enthusiastic and say all the wonderful things about v6. More addresses, more efficient routing, ICMPv6 is a lot cleaner, DHCPv6 is a lot cleaner, subnet plans can suddenly be sane. I get to say all those things. And there are some things that everyone says is it's more secure because. Well, okay, subnets. You can't brute force scan 18 quintillion addresses in a practical time frame. We have privacy addresses, makes life better. And IPsec is no longer an afterthought. IPsec is built in. You're going to hear these all the time. And to some degree, they are true. But there is the reality. Bad host numbering schemes will defeat brute force scanning. And servers. There was a fascinating paper with the IEEE where they went through DNS, they went through log files, and they used things like subnets with DEAD or CAFE or all the cute little things that we all use for our subnet names because we can. And the fact that people do things like take their v4 address and stick it on the end of a v6 prefix and all sorts of other things. And they proved that for servers, they could find 95% of the servers without having to get onto link local and use link local to discover. On the other hand, servers are supposed to be findable. If you can't find your web server, it's not a very useful web server. If nobody can find your mail host, then you're not going to be getting a lot of mail. So to some degree, it's just validating that what you're supposed to have as findable is. But it also shows that there are any number of lazy or sloppy habits that we can inject that will lower the efficacy of our numbering schemes and security. And IPsec, it's another one of those good news, bad news. Good news is that if you're already doing IPsec for IPv4 and you're already doing shared secrets, and you're pre-configuring the client, and you're pre-configuring your termination or aggregation point to know about that client, you can do exactly the same thing, use the same procedures and provisioning processes now in v6, and it works just the same. Bad news is, it is not at all better than v4. It should be, and it isn't. And the missing piece is PKI, public key infrastructure. Currently, the IETF seems incapable of coming to a consensus, nor are the vendors capable of coming to a consensus on what a usable PKI infrastructure should be. So since you can't use a PKI to hand out a secret securely to a client, you have no way of doing anything other than pre-configuring. The sole exception, sadly enough, is Microsoft. Microsoft actually has done the earliest, best, most robust, most RFC compliant IPv6 stacks of any end host environment, bar none. They are worlds ahead of Apple at this point, and they are even ahead of the Unix guys in terms of being RFC compliant and getting v6 into everything. And they're very serious about it. And they have the only actual real usable IPsec application on the market that uses IPsec the way it really should be. Microsoft, with their Windows AD authentication, is effectively Kerberos under the hood. So when you get your little login with, my domain / my user and my password, I get a ticket granting ticket from the server. That ticket granting ticket can be used to encrypt other keys and other secrets that I can then use to configure myself for other services, including direct access. One of the other interesting things out there is that Teredo is a tunneling technology that works through NAT, works through firewalls. It looks like a v4 bit stream. Kind of cool, kind of scary. But in this case, what happens is I, as the user, I'm out in a hotel or at a convention, and I do my Windows login. Not only do I get a ticket back that gets me into Outlook and all of my happy horseshit there, it gets me a little ticket that says, and your direct access credential is this. I then make a Teredo IP6 tunnel, which is IPsec encrypted, all the way from my box, all the way to a Windows 2008 server at the other end. And suddenly I'm in that local domain, and I can browse and see all of the services that would normally be offered as if I were on the local network. And the only difference is latency. And I didn't change my configuration on my box. Yes, you do have to pre-configure on the 2008 side to tick the little box to say, yes, they can do direct access. But it's pretty trivial. And then I can go through any firewall, any hotel NAT, anything else, and it's all encrypted, and it's completely transparent to the user. Because they have PKI. And my hope is that if Microsoft can do it right, God, I hope that anybody else can do it right. So that is the reality right now. So one of the things that you should be doing right now, even if you're not rolling out IP6 as we speak, is to prepare for it, you should be making sure that all of your perimeter devices actually deal with IPv6. Because in the magic world where everything is rainbows and unicorns, every single device we have on our internal network is individually hardened and patched and up to date and secure, and our perimeter is additional layers of protection beyond those. In the reality we live in, we have a hard and crunchy outer shell, and everything else is soft and gooey center. And if you get past our perimeter devices at all, it's all soft goo. Which means that little things like Teredo that magically tunnel through, it looks like a bit stream. Remember I was talking about BitTorrent and Facebook and how do we know, and it just looks like data packets. Teredo just looks like data packets. Doesn't have a particular well-known set of IPv6 addresses that I can filter my ACLs. Doesn't use a well-known port. Doesn't use a well-known TCP protocol number. And those are the three knobs that you pretty much have for all ACL-based rules. If you can't filter by address, port, or protocol number, you are reduced to signature-based detection. And if you can't detect a tunnel, even though in theory you can disable Teredo on the client with group policy, if your clients themselves or your users have admin privileges on their box, which many engineers and sophisticated users demand, and I set up a bad web page, I'm betting it's not terribly hard to come up with a web page that would run some kind of Java code that would go in, twiddle my registry, turn Teredo back on, and open up a Teredo tunnel to my bad person Teredo tunnel terminator at the other end. And I now have a path that is invisible to you through your firewall to your trusted host. And you are done, unless you can catch it. And so my homework for all of you is to go to all of your vendors and say, I would like to run a test with your device. And I will stick a box behind this device, and I will set up a Teredo tunnel server out on the internet. And I will open up a tunnel, and I will wait to see that error dialog or alarm box that your stuff pops up to show that I've done this. And if not, I'm going to be filing bug reports for not buying your stuff. Because if we don't start asking now, if they don't have it, it's 6 months to a year before you see it in production. Most of us are going to have to do something with V6 in the next 18 to 24 months. Doesn't give you a lot of time for them to get their shit together. So start beating on them now. And the more people that do it, because the other excuse is, oh, nobody's asked us about V6, so we haven't done it yet. And they're not going to start until somebody asks, at which point they're a year behind the curve. So help them do the right thing. And the other piece is make sure that all of your own monitoring and logging stuff handles it. Do you have Perl scripts that grovel through your syslog files? Do they have fixed data sizes in which you stick IP addresses that are 32 bits long? Because they'll probably be unhappy with 128 bits. If you are using a commercial network monitoring system or similar logging or fancy whizzy stuff, make sure that they have not hard-coded things or have database entries that have things that don't fit V6 values. There are unique things. ICMP V6 has changed. DHCP V6 has changed. You want to make sure that all of your stuff is there. You want a new test. It used to be you just looked, is my pool exhausted? That was my problem. Well, now it's have I used 1% of my 18 quintillion addresses? If I have, I want an alarm in my NOC. Because 1% of that is millions, or billions, or some really large number of addresses used. Make sure that you can actually see what's going on. So that's the broad strokes. I'd like to take questions. Pretty much anything that you have.
You touched on the security stuff. What about rogue RAs and rogue DHCP V6?
Okay, rogue RAs and rogue DHCP. They are functionally equivalent. There are some changes. In order to be a rogue RA or a rogue DHCP, one of the barriers to entry that wasn't there is at least you also have to get onto the link local of every domain to be able to corrupt it. In the old days, the relays would happily filter it, and as long as you could capture the packet or inject a packet back anywhere in the stream, you were at risk. So it's fractionally better in that regard, but the risk and the mitigation are similar in that, yes, if you succeed in being able to be a rogue RA or a rogue DHCP server, you get to play man in the middle. Because one of the things you do is, if I were going to be a bad person and I were doing a rogue RA, the first thing I would do is I would set the lifetime of my route to infinite. I would set my priority to the most desirable, and I would set the router default gateway to me. And I would try and do a DHCP reconfigure just to see if it happened to work, to rush the process along. So, and then basically you're stuck at man in the middle is ultimately the issue. Other questions?
Are vendors talking much about the performance differences between V6 and V4?
Performance differences from the vendors. No, they're not much. At the large iron level, they are getting to the point where, initially the efficiencies in routing and packet header processing weren't as great in v6 because it was still CPU switched, it was in software. Pretty much all of the big router and switch vendors have gotten to the stage where that's now actually down in the ASIC. And there have been some performance tests that have shown that you can, in a pure v6 network, truly shovel off more packets. They are not pushing it yet, sadly. The other thing to consider also is that that's really nice, but you essentially still have to deal with v4. So right now, they're burning a lot of RAM on the cards and space on the cards, dealing with the fact that they have to do dual stack. When you can get to the point where you can do some kind of transition at the edges and more of your core internal is v6 only, I think is when we're going to start to see some of the real performance increases, and when they can start to leverage things like flows and actually get QoS that actually functions as a quality of service as opposed to a feeble wish that you hope kind of works.
That might be a little bit out of scope for this discussion, but I wanted to find out more about, say, IGP, OSPF v3 versus ISIS, or anything else you might have heard, or maybe which one's better in your
Okay, IGP differences. Actually, I'll do IGP and EGP differences. This is the right crowd for it. The quick answer is that BGP for an EGP has been capable of dealing with IPv6 for years now, and it's stable, and it works the same way as long as you're using anything vaguely current on any of the large boxes. Instead of 31s and 32s, you're going to have 127s and 128s, but that more or less works. And your iBGPing also similarly, if you're already doing it by carrying loopbacks around, that'll work. Most people wind up carrying the loopbacks in an IGP. The two real choices, there is a RIP-NG because the internet never throws away a really bad idea ever. But ISIS was originally written with an abstraction layer. Functionally speaking, OSPF and ISIS are link state flooding algorithms, and they are functionally very similar. There's an abstraction layer in ISIS, there's area 0 in OSPF, but functionally they are speaking. So in v4, normally when somebody asks me, my response is, culturally, if you're used to OSPF already, use OSPF. If you're culturally used to ISIS, use ISIS. And in general, where you're going to see backbone and providers are going to be more likely to use ISIS. Folks that are anycasting or doing host-based are more likely to be in OSPF. That's the general case. That's v4. In v6, things have shifted. Because of the fact that ISIS was written specifically to be protocol agnostic, because it was designed to handle IP and CLNS, OSI, CLNS, both, it already had an abstraction layer. So ISIS works quite cleanly. And you can run a v4 and a v6 routing process in the same ISIS instant in the same RIB. OSPF was written with overly intimate knowledge of IP. And I do mean exactly what you're thinking when I say overly intimate knowledge of IPv4. So when they tried to do IPv6, they essentially had to do something that looked like it from the outside but was completely different internally. The result is that OSPF v3 usually cannot run in the same process. So if you're doing v4 and v6, you will have two sets of RIBs, you will have two processes running on your router simultaneously, and you will take up double the memory that you would with just running v4 or v6. There is an RFC, which I can't recall the number of offhand, and Cisco supposedly has working code for having a melded v4 and v6 in a single OSPF process. I have not been able to find through normal TAC access if it's usefully deployed in most code bases. It does not seem to be. So, on the other hand, most people who are doing OSPF, they are doing things like they're throwing around a bunch of 32s, or they're doing loopbacks or something else relatively small. So running two processes probably isn't hugely expensive. And if you're already running OSPF, and again, culturally you're comfortable with that, then go with that. If you're already running ISIS, go with that. The other new thing is, if you were truly starting from ground zero, have no cultural bias either way, and you're trying to pick and you know you're doing v6, I would recommend ISIS because it is more solid in a single process right now. Other questions? Another, oh, go ahead.
Talk a little bit about the SLAC versus DHCP. What about like equivalent for PPP as far as host authentication for DSL provider, cable provider?
Okay, so user authentication such as PPP for a DSL provider, what it really boils down to is just as what now happens is your DHCP server is usually hacked to do CHAP or PAP or PPP or some other unholy database lookup based on usually MAC address. And then based on all of those things, it will make a decision as to how it cans out an address. If you were doing that kind of provisioning in v4, then what you'll probably wind up doing is you won't want to do SLAC. You don't want clients to pick their own addresses because they don't come out of your pool and you don't know about them. And you don't tie them to a particular user. So what you'll do instead is you will advertise a prefix but set the A flag or autonomous address flag to off, saying don't auto-config anything on yourself, so you'll only auto-config a link local address. And get a default gateway, because you can't get that in DHCP, but then set the O and the M flags to on and have all of the other stuff go up to the DHCP server. And then again, you can hack the DHCP server to do the authentication. The missing piece right now is that currently, the way most of those work is there's an HW adder field that can be sent by the relay or by the client, which is your hardware address or your MAC address. So not only do you get it in the broadcast, because that happens as part of DHCP and v4 because it's a broadcast-based layer 2 exchange, it also hands you the MAC address which the server can then use. Currently, there is no HW adder field support in DHCP v6. There is an IETF draft that is likely to pass, hopefully in Paris next month, that would allow a server to then get that. Once you update the client, which of course in most cable or DSL providers, they're dictating what CPUs are acceptable. And they also control their own server. So that's effectively what you do. You would get the hardware address again, and then you would use that as your key. You do your lookup by whatever means. And then if you're truly doing the layer 2 or 1.5 to 2 PPP stuff first, that still works. Just in the same way that walled gardens. Currently, if you go into a walled garden where it looks at your MAC address and says, you hit the first switch port and it says, I have not been told that using this MAC address is okay, it will then stick you into usually a 1.0 something network where you go to some web page, you will do your magic stuff and all the normal hotel stuff, and then after you've paid your money and taken your chances, it will then give you a usable address and say that MAC address is okay, and it will turn off MAC filtering for that switch port. Currently, there's no convenient way to do that with v6, but if you're dual stacking, MAC address is the same in both cases. So once you've done the walled garden in v4, all the v6 stuff will go through fine. And I suspect that, again, is going to be what most of the providers are going to do for walled garden now. Eventually, when v4 is much less common and v4 gear is less common, that's going to be another thing that the IETF will have had to have thought of how to get around. So, other questions? Yeah, so carrier grade NAT and NAT 6.4. Well, the first thing I'll say is that large scale NAT or carrier grade NAT is an interesting story in the same category as the Easter Bunny. It's really lovely and we all get candy, so we're willing to put up with it, but it isn't really very real. It is getting used right now. The biggest place where you'll see it is a lot of the new 4G and LTE wireless networks are going v6 only. And the way they are getting you to the v4 internet is that they are using a carrier-grade NAT solution. There are some things that the providers know and hope that the public doesn't know or won't figure out soon. Because Carrier grade NAT is insanely expensive. We're talking millions of dollars of hardware that doesn't really do a great job, doesn't scale well, and will only be usable for a few years before something else happens. So already they don't like it because they can't amortize it over 10 years and pass on the cost to their customers. And the reason they're getting away with it right now is that most handsets are not capable of sufficient bandwidth usage to truly tax, because they can't, and the providers have priced it such that it is painful for you to do it financially. And most of the applications that most of us are running are not bandwidth intensive either, because streaming video to a 4-inch screen is a not terribly usable experience. And finally, most folks are not catching on to it, because if one website sucks in performance and another doesn't, most users are programmed to think, the cellular network is just dropping right now because cellular networks suck. Most people are not sophisticated enough to figure out, I went to a V6 native site and got good performance, I got to a V4 site and my performance sucked, and be able to make that correlation. As more and more tablets are used and bandwidth of application goes up, and things like gamers who actually pay attention to V4 and V6 and jitter and packet loss and lots of other things because they can't shoot as many bad guys, they will get it on the bulletin boards and people will notice, and they will start saying that the carrier-grade NAT Emperor is naked. So it is a technology that will solve some problems for some period of time. I don't think that anyone thinks it will be the solution. And anybody who has a clue doesn't think it's going to be an acceptable solution for very long. Now, that said, for things like NAT 6.4 and other forms of NAT for specialized application, there are a lot of things that we have. You know, when I talk to people and they say, what do I need to do to be sure I'm ready for V6? And you know, most people say, check all your switches and all your routers because it's IP and it's a networking thing. So check all your networking gear. And some people are savvy enough to go check all your OSs. I usually say anything that spits packets on some form of network and runs on some form of power needs to be validated, which means things like badge card readers, smart power strips, wireless video cameras, that AS400 that hasn't been touched since Y2K that does your payroll. And some of those are things that we are not going to be able to replace and that will never be upgraded to V6. So there will be some things for which these transition technologies will be transitioned until they die. But the odds of a NAT 6.4 on modern hardware being able to keep up with the amount of traffic that an AS400 shovels doing payroll, pretty damn good. So in the right places, knowing what the problems are and what the problems you're trying to solve, NAT is certainly something that we are going to be using. And in the same way that currently there's something called NAT-PT, which is prefix translation, which is the IETF's claim as to why we won't need NAT 6.6. NAT-PT says I take one prefix off of the front of the address and I stick a different prefix on, which is not what most people consider NAT 4.4 or NAT 6.6, because there is no one public address to multiple private addresses, which is the alleged security benefit of NAT. So NAT-PT is not going to solve that problem. So users are going to demand NAT 6.6, and the same people who filter all ICMP and who go NAT is evil and say TCP 53 is just broken are going to be sitting there going, NAT is a security requirement, not a feature, but a requirement, and they're going to wave a check and someone is going to happily take their money. So we will have NAT, and as long as we know where and how it sucks and where it's a viable solution, it will function for some definition of function. Other questions? So last lobby for you guys. If you are not already running on an IPv6 network, the best way to learn is to get your hands dirty at home. Get a tunnel from either Hurricane Electric or 6X, SIXXS. Both will give you tunnels for free. And get DHCP and an RA running at home. There are Linux and Unix variants for the servers that will work just fine. It's all free. All it takes is your time. And the best thing you can do is get up an RA, DHCP server, and a bunch of clients, and a tunnel, and see what happens. And if you have any questions, the slides have my email. Go ahead and hit me up later, or find me here.
I might also suggest that your ISP might be running a beta.
Yes.
IPv6, so.
Yes, there are ISPs that are starting to beta, notably Comcast right now. AT&T has started for their wireless. There are rumors that Verizon will be launching, and T-Mobile has just started a V6 trial in the Bay Area and I think one other city. So definitely if you can get those. Native is going to be better performance. Tunnels are an encapsulation or translation method. They have inherent overhead. I have 6x at home, and I'm grateful for it because it's the only thing I can get that works through double NAT. But my V6 packets over the exact same network path as V4 to that first pop take a 70 millisecond per packet penalty in performance. So I am thoroughly enjoying the V6 connectivity here versus home. Any other questions? Well, thank you very much.